Uranus looked dead. For decades, every telescope that turned toward the seventh planet saw the same thing: a featureless blue-green ball drifting through the outer solar system in silence. No storms. No detail. No drama. Scientists treated it as the boring planet, the one you skip in the documentary. Then in 2023, the James Webb Space Telescope aimed its golden mirror at this frozen world and captured something nobody expected. Rings that had been invisible suddenly blazed with detail. A glowing polar cap revealed weather patterns no model had predicted. And when astronomers mapped its upper atmosphere in 3 dimensions for the first time, they discovered auroras twisted by the strangest magnetic field in the solar system, and a planet that has been mysteriously cooling for 3 decades, with no explanation. Uranus was never dead. We were just blind. If you want to find out what the most powerful telescope ever launched revealed about the most neglected planet in our solar system, go ahead and hit that like button and subscribe. It genuinely helps the channel grow and lets us keep making these deep dives for you. Let's begin. There is a planet in our solar system that most people forget exists. It sits nearly 2 billion miles from the Sun, locked in a slow, frozen orbit that takes 84 Earth years to complete. It has no dramatic red spot like Jupiter, no spectacular rings like Saturn, no romantic rust-coloured deserts like Mars. When the most advanced spacecraft humanity ever sent to the outer solar system flew past it in 1986, its cameras returned images of what appeared to be a perfectly smooth blue-green marble. No storms, no bands, no visible features of any kind. Scientists looked at those images and essentially shrugged. Uranus became the planet you skip in the documentary. The one teachers rush past on the poster. The cosmic afterthought that exists somewhere out there in the dark between Saturn and Neptune, doing apparently nothing. That reputation stuck for nearly 4 decades. And it was almost entirely wrong. To understand why Uranus was so profoundly misunderstood, you first need to understand what kind of world it actually is. Uranus is the 7th planet from the Sun. It is classified as an ice giant, a category it shares only with its neighbour Neptune. The term ice giant is somewhat misleading. It does not mean the planet is a frozen ball of solid ice. It means the planet's bulk composition is dominated by heavier volatile compounds, water, ammonia, and methane, existing under extreme pressures and temperatures in states that do not correspond to anything in everyday human experience. Deep inside Uranus, water molecules may be crushed into a strange electrically conducting fluid. Methane may be squeezed so hard that it releases carbon atoms, which could compress into diamonds that rain through the interior like hailstones sinking through a furnace. The term ice in planetary science refers not to temperature, but to composition. These are worlds built from substances heavier than the hydrogen and helium that dominate Jupiter and Saturn, and that chemical difference makes them fundamentally different kinds of planets. Uranus is large by any human standard. Its diameter stretches roughly 31,500 miles, making it about 4 times wider than Earth. If Uranus were hollow, you could fit approximately 63 Earths inside it. Its mass is about 14.5 times that of Earth. Despite that size, it is the least dense of the giant planets after Saturn, a clue that its interior contains large quantities of lighter icy materials, rather than the metallic hydrogen cores that make Jupiter and Saturn so massive. The surface gravity on Uranus, if you could somehow stand on its cloud tops, would be roughly 89% of what you feel on Earth. You would weigh slightly less there than you do here, standing on the edge of an abyss of swirling gas and compressed fluid thousands of miles deep with no solid ground beneath you at any depth. But the single most defining characteristic of Uranus, the feature that makes it unlike any other planet in the solar system, is its axial tilt. Every planet rotates on an axis, an imaginary line running through the north and south poles. Earth's axis is tilted about 23.5 degrees from vertical relative to the plane of its orbit. That modest tilt is what gives us seasons. Jupiter's axis tilts only about 3 degrees, so it barely has seasons at all. Uranus is tilted 97.77 degrees. It is essentially lying on its side. Some astronomers describe it as rolling around its orbit like a ball, with its poles alternately pointing almost directly at the Sun and then away from it. No other planet does this. The leading hypothesis is that sometime during the early chaotic period of solar system formation, roughly 3 to 4 billion years ago, a protoplanet roughly the size of Earth slammed into Uranus with enough force to knock it onto its side. That single catastrophic impact may have defined nearly everything strange about this world. Its tilt, its retrograde rotation, its peculiar internal heat distribution, and possibly even the extreme offset of its magnetic field. The consequences of this tilt are extraordinary. As Uranus orbits the Sun once every 84 Earth years, each pole spends roughly 42 years tilted toward the Sun in continuous daylight, followed by 42 years facing away in continuous darkness. Near the solstice, one pole stares directly at the Sun while the other faces the black void of deep space. The equatorial region at that time receives sunlight at an extreme angle, almost like twilight that lasts for decades. Then, as the planet moves through its orbit toward equinox, the geometry shifts so that the equator faces the Sun, and both poles receive roughly equal illumination. These are not subtle seasonal variations like Earth experiences. These are the most extreme seasons of any planet in the solar system, cycles of heating and cooling that play out over human lifetimes, reshaping atmospheric circulation on timescales we have barely begun to observe. This is one of the fundamental problems with studying Uranus. We have never watched a full Uranian season with modern instruments. The planet was discovered on March 13, 1781, by the astronomer William Herschel, a German-born musician turned telescope builder living in Bath, England. Herschel was not looking for planets that night. He was conducting a systematic survey of the sky, cataloguing double stars and nebulae using a homemade reflecting telescope with a mirror he had ground and polished by hand. When he pointed his instrument toward the constellation Gemini, he noticed an object that did not look quite right. It was not a sharp point of light like the surrounding stars. It appeared as a small disk, slightly fuzzy at the edges. Herschel initially recorded it as a comet and reported the finding to the Royal Society. Over the following weeks, other astronomers tracked the object's motion and attempted to calculate a cometary orbit. The math did not work. Comets travel on elongated, eccentric paths through the solar system. This object moved on a nearly circular orbit far beyond Saturn. It was not a comet. It was a planet, the first discovered with a telescope, the first found since the ancient civilizations had identified Mercury, Venus, Mars, Jupiter, and Saturn thousands of years earlier. Herschel proposed naming it Georgium Sidus, the Georgian star, after King George III of England. The international astronomical community declined that suggestion. The German astronomer Johann Elert Bode proposed naming the new world after the Greek god of the sky, Uranus, the father of Kronos, who was the father of Zeus, maintaining the mythological lineage of the existing planetary names. The Latinized version, Uranus, eventually stuck, though it took decades for the name to gain universal acceptance. The discovery doubled the known size of the solar system overnight. Saturn had been the outermost known planet for all of recorded human history. Suddenly, there was another world beyond it, orbiting in cold darkness at a distance that strained the imagination of 18th century astronomers. Yet even after its discovery, Uranus remained stubbornly mysterious. It was too far away and too faint for the telescopes of the era to reveal any surface detail. For more than 2 centuries after Herschel spotted it in his handmade reflector, Uranus remained little more than a pale dot in the eyepiece. A world whose existence was confirmed, but whose nature was almost entirely unknown. Since that moment, Uranus has completed fewer than 3 full orbits around the Sun. We have had telescopes capable of resolving any atmospheric detail for less than 1 of those orbits. We are trying to understand a planet whose weather changes on timescales of decades, using observations that span, at best, a few years at a time. It is like trying to understand Earth's climate by looking out the window for 30 seconds. And even during those brief observational windows, Uranus has been maddeningly difficult to see. The reason begins with distance. At its closest approach to Earth, Uranus is still approximately 1.7 billion miles away. At its farthest, it is nearly 2 billion miles away. Sunlight takes about 2 hours and 40 minutes to reach Uranus, compared to about 8 minutes to reach Earth. That enormous distance means Uranus appears incredibly small and faint in telescopes. Through a modest backyard telescope, it looks like a tiny pale dot barely distinguishable from a star. Even through the largest professional ground-based telescopes, the planet's disk is small, and atmospheric turbulence smears the image, washing out fine detail. Adaptive optic systems, which use deformable mirrors to counteract atmospheric distortion in real time, have helped enormously. The Keck Observatory in Hawaii has captured some useful images of Uranus using this technology, but the resolution is still limited compared to what close-range spacecraft observations can provide. The Hubble Space Telescope, orbiting above Earth's atmosphere, offered a major improvement. Hubble observed Uranus repeatedly over a span of more than 20 years, tracking seasonal changes in the polar hazes and capturing occasional bright cloud features. Those observations revealed that Uranus is not as featureless as Voyager 2 suggested, though extracting detail from such a distant target required patience measured in years. In the early 2000s, as Uranus approached its equinox in 2007, Hubble began detecting bright cloud features in the planet's atmosphere for the first time from Earth orbit. These were not the faint, marginal detections that ground-based telescopes had occasionally reported. They were distinct, compact, bright features visible in near-infrared images, evidence of convective activity punching through the upper atmosphere. As equinox arrived and the sun illuminated the planet's equator directly for the first time in decades, the weather intensified. Storms appeared at multiple latitudes. A dark spot, reminiscent of Neptune's Great Dark Spot, observed by Voyager 2 in 1989, was detected in Uranus's atmosphere in 2006, providing the first evidence that Uranus could produce the large-scale vortex structures common on other giant planets. The equinox period also offered a rare geometric opportunity. With the rings-oriented edge onto Earth, astronomers could observe ring features and search for faint outer rings that are invisible when the system is tilted at other angles. Hubble detected additional faint ring components during this window. Over the following decade, as the North Pole tilted increasingly toward the Sun, Hubble tracked the gradual brightening of the North Polar Cap. The polar haze grew more prominent year by year, a seasonal aerosol response to prolonged solar illumination at high latitudes. Spectroscopic observations revealed that methane, the gas responsible for the planet's blue-green color, was notably depleted near both poles compared to equatorial regions. This depletion persisted throughout the 20-year monitoring period, suggesting it was a fundamental feature of the atmospheric circulation rather than a temporary weather pattern. The polar regions appeared to be zones of downwelling, where air descends from higher altitudes, pushing methane-poor air from the upper atmosphere down to levels where it could be detected spectroscopically. These Hubble observations painted a picture of a planet with genuine atmospheric dynamics, seasonal variability, and hemispheric asymmetries that evolved on timescales of years to decades. But they also highlighted the limits of what could be achieved without deeper infrared capability. But Hubble operates primarily in visible and near-ultraviolet wavelengths. It can see the upper cloud layers and the methane haze, but it cannot peer deep into the atmosphere or resolve the faint ring system with the kind of clarity needed to truly understand the planet. For that, you need infrared, deep, sensitive, space-based infrared, and for decades no such instrument existed with sufficient power to reveal what Uranus was hiding. There is another reason Uranus remained so poorly understood for so long. Its most dramatic features are nearly invisible. In 1977, astronomers James Elliott, Edward Dunham, and Douglas Mink were using the Kuiper Airborne Observatory, a telescope mounted inside a modified cargo aircraft, flying above most of Earth's atmosphere to observe Uranus as it passed in front of a distant star. The technique is called stellar occultation, and it allows astronomers to study a planet's atmosphere by watching how starlight dims and flickers as it passes through the gas on its way to Earth. What nobody expected was what happened before and after the star disappeared behind the planet itself. The starlight blinked, 5 times before the planet blocked it and 5 times after, in a perfectly symmetrical pattern. Something was orbiting Uranus in thin bands, blocking the starlight briefly as each band passed between the star and the telescope. Uranus had rings. 5 were confirmed in that first observation, and subsequent occultation studies over the following years brought the total to 9. All of them were thin, dark, and composed of particles so unreflective that no telescope had ever seen them directly. Unlike Saturn's broad, bright, icy rings that practically announce themselves from across the solar system, the Uranian rings are narrow and dark, made of material that absorbs most of the light that hits it. They were invisible in every photograph ever taken of the planet. Only the indirect method of watching a star wink out behind them revealed their existence. This discovery hinted at a broader truth about Uranus that would take decades to fully appreciate. The planet was not featureless. Its features were simply too faint, too dark, and too far away for existing instruments to detect. So for most of its modern history, our understanding of Uranus has rested on a single event. One flyby, one spacecraft, 6 hours. On January 24th, 1986, NASA's Voyager 2 spacecraft passed within roughly 50,600 miles of Uranus's cloud tops. It was the culmination of a grand tour trajectory that had already carried the probe past Jupiter in 1979 and Saturn in 1981. The encounter was brief but productive. Voyager 2 discovered 10 previously unknown moons, bringing the total at that time to 15. It found 2 additional rings, adding to the 9 that had been discovered from Earth in 1977 through stellar occultation observations. It measured wind speeds, atmospheric composition, and the temperature of the upper atmosphere, which registered at approximately -353 degrees Fahrenheit, making Uranus the coldest planetary atmosphere in the solar system. But the most startling discovery was the magnetic field. Earth's magnetic field is generated by convective currents of liquid iron in the outer core. It aligns roughly with the planet's rotational axis, which is why compass needles point approximately toward the geographic poles. Jupiter and Saturn follow similar patterns, with magnetic fields roughly aligned to their spin axes. Uranus broke the pattern completely. Voyager 2 found that the Uranian magnetic field is tilted nearly 60 degrees from the planet's rotational axis and offset from the planet's geometric center by about 1/3 of the planet's radius. This means the magnetic field does not emerge symmetrically from the core. It is lopsided, skewed, and as the planet rotates every 17 hours, the entire magnetosphere wobbles through space like a poorly thrown football. Scientists had never seen anything like it. The prevailing models of planetary magnetic field generation could not easily explain how such a configuration could exist. It implied that the field was not being generated deep in the core, as it is on Earth, but rather in a thin shell of electrically conducting fluid at an intermediate depth, perhaps a layer of compressed water mixed with ammonia and other ionic compounds. This was a fundamentally different kind of planetary dynamo, and 4 decades later it is still not fully understood. The moons proved equally surprising. Voyager 2 returned detailed images of the 5 major Uranian satellites, and the smallest of them stole the show. Miranda, barely 300 miles across, a moon so small it should have been a geologically dead ball of ice and rock, displayed one of the most tortured landscapes in the solar system. Enormous canyons sliced across its surface, some of them 12 miles deep, more than 10 times the depth of the Grand Canyon on Earth. Vast regions called coronae featured concentric ridges and troughs that looked like racetracks carved into the ice. Fractured terrains of wildly different ages and textures sat side by side as though the moon had been assembled from mismatched pieces. One leading hypothesis suggested that Miranda had been shattered by a massive impact and then gravitationally reassembled, its fragments falling back together in a jumbled configuration. Another proposed that tidal heating from gravitational interactions with Uranus and the other moons had driven internal geological activity, pushing material up from below and fracturing the surface. Either way, Miranda was not the dead world scientists had expected. Even Ariel, the next moon outward, showed signs of relatively recent geological resurfacing, with smooth plains and extensive valley systems that suggested internal processes had been at work in the geologically recent past. These hints of activity would take on new significance decades later, when the question of subsurface oceans at Uranian moons entered the scientific conversation. Voyager 2 also observed something deeply puzzling about the magnetosphere's contents. Inside the magnetic bubble surrounding the planet, the spacecraft detected intense radiation belts with electron energies second only to Jupiter's ferocious radiation environment. But the rest of the magnetosphere was nearly devoid of plasma, the hot charged particles that typically fill planetary magnetic fields. This was strange, because the 5 major Uranian moons, encased in ice, should have been producing water ions through interactions with radiation and micrometeorite impacts. Just as the icy moons of Jupiter and Saturn do, scientists concluded at the time that the moons must be geologically inert, producing no detectable material. Uranus earned another mark in the boring column. Then, in 2024, a study published in the journal Nature Astronomy by Jamie Jasinski of NASA's Jet Propulsion Laboratory revealed something that rewrote the story entirely. By carefully reanalyzing the original Voyager 2 magnetometer data, plotting new data points every 1.92 seconds instead of the broader averages used in the original analysis, Jasinski and his team discovered that Uranus had been hit by an intense burst of solar wind in the days just before Voyager 2 arrived. This solar wind event dramatically compressed the planet's magnetosphere, squashing it inward, driving plasma out of the system, and supercharging the radiation belts with energized electrons. The spacecraft had arrived during conditions that occur only about 4% of the time. It was a cosmic coincidence of the worst possible kind for science. Nearly everything Voyager 2 measured about the magnetospheric environment was shaped by this anomalous event. The missing plasma, the unexpectedly intense radiation belts, the conclusion that the moons were inert, all of it was potentially a consequence of the solar wind compression, rather than the normal state of the Uranian system. As Jasinski stated, if Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere. Linda Spilker, a Voyager 2 mission scientist who was present during the original flyby, acknowledged that the magnetosphere Voyager 2 measured was only a snapshot in time. 4 decades of scientific interpretation had been built on that snapshot. The conclusions drawn from it had filtered into textbooks, review papers, and planetary science models. And now those conclusions were being called into question, not because the data was wrong, but because the timing was extraordinary bad luck. This revelation carried an additional implication that excited astrobiologists. If the missing plasma was not evidence of dead, inert moons, but instead the result of a temporary solar wind event, then the Uranian moons might actually be geologically active. They might be producing water ions. They might, beneath their icy crusts, harbour liquid water. The possibility was speculative, but could not be dismissed. Uranus's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, suddenly re-entered the conversation as potentially interesting worlds worthy of dedicated exploration. By the early 2020s, the scientific community had reached a clear consensus. We did not understand Uranus. Our single flyby had been compromised by bad timing. Our ground-based observations could not resolve the detail we needed. Our space telescopes lacked the infrared sensitivity to penetrate the methane haze and study the deeper atmosphere, the ring system, and the magnetic environment in the ways that mattered. In 2022, the National Academies of Sciences, Engineering, and Medicine released its Planetary Science and Astrobiology Decadal Survey for the period 2023 to 2033. This document, produced every 10 years, represents the collective scientific priorities of the planetary science community. It recommends which missions NASA should pursue in the coming decade. The number one priority for a large strategic mission was a Uranus orbiter and probe. Not Mars, not Europa, not Enceladus, Uranus. The survey explicitly identified the ice giants as representing one of the most significant gaps in our understanding of the solar system. The report called for a spacecraft that would orbit Uranus for years, deploy an atmospheric probe to measure composition directly, map the gravitational and magnetic fields, study the ring system up close, and investigate the moons for signs of geological activity and potential habitability. The projected launch window would be in the early 2030s, with arrival at Uranus around the early 2040s, but a dedicated orbiter was at minimum a decade away, possibly longer given budget constraints and the narrow launch windows dictated by planetary alignment. The ice giant was not going to receive a visitor anytime soon, and yet the planet was approaching a critical moment in its seasonal cycle. Northern summer solstice was expected around 2028. The polar cap was brightening, atmospheric dynamics were shifting, the planet was changing in real time, and the only way to watch those changes unfold was from a distance of nearly 2 billion miles. What the scientific community needed was a new kind of observation, something more powerful than Hubble, something that could see deeper into the infrared, resolve finer detail, and operate from a stable platform above Earth's atmosphere with uninterrupted viewing. Something that could reveal the rings, the storms, the auroras, and the atmospheric structure that had been hidden for so long behind a curtain of methane haze and cosmic distance. By the end of 2022, such an instrument had just completed its commissioning phase and was beginning to turn its attention to targets across the solar system and beyond. It was the largest, most powerful, most expensive space telescope ever built, and when it finally looked at Uranus, everything we thought we knew about the forgotten planet began to unravel. Everything we had believed about Uranus for nearly 40 years came from a 6-hour flyby during a 1 in 25 cosmic coincidence. A new set of eyes, the most powerful ever placed in space, was about to look again, and the planet that had been dismissed as boring was about to prove just how wrong we had been. The telescope that would change everything nearly did not survive its own birth. The James Webb Space Telescope spent more than 2 decades in development, endured countless budget overruns, weathered multiple threats of congressional cancellation, and arrived at its final price tag of roughly $10 billion, making it the most expensive scientific instrument ever constructed. Originally planned for launch in 2007, it was delayed again and again as engineers wrestled with unprecedented technical challenges. The primary mirror alone required a fundamentally new approach to space telescope design. At 6.5 meters across, it was far too large to fit inside any existing rocket fairing in a single piece. So engineers designed it to fold. 18 hexagonal segments, coated in a microscopically thin layer of gold, would launch compressed together, then unfurl in space like a mechanical flower, each segment adjusting its position with nanometer precision using tiny actuators on the back. If even one segment failed to deploy correctly, the telescope would be crippled. If the sun shield, a 5-layered membrane the size of a tennis court designed to keep the instruments at operating temperature below -370 degrees Fahrenheit, failed to unfold properly, the entire mission would be lost. There were over 300 single points of failure during deployment, 300 moments where one stuck latch, one jammed motor, one misaligned cable could have turned a decade of work into orbiting debris. On December 25, 2021, an Ariane 5 rocket lifted off from French Guiana carrying the folded telescope into space. Over the following 2 weeks, the world watched as each deployment step succeeded. The sun shield unfurled, the secondary mirror swung into position, the primary mirror segments unfolded and locked into place. Engineers at the Space Telescope Science Institute in Baltimore began the months-long process of aligning the mirrors and cooling the instruments to their operating temperatures. By the summer of 2022, the James Webb Space Telescope was fully operational and delivering its first images. The results were immediately and obviously superior to anything that had come before. To understand why Webb was about to transform our understanding of Uranus specifically, you need to understand what makes this telescope different from its predecessors. The most important distinction is wavelength. The Hubble Space Telescope observes primarily in visible light and near ultraviolet, the same wavelengths the human eye can detect plus a bit beyond. Webb was designed from the ground up as an infrared observatory. Its instruments are optimized to detect light at wavelengths ranging from roughly 0.6 to 28 microns, deep into the infrared spectrum far beyond what human eyes or Hubble's cameras can see. This matters enormously for planetary science because different wavelengths reveal different things. Visible light shows you the top of the methane haze on Uranus and not much else. Infrared light at carefully chosen wavelengths can penetrate that haze, revealing cloud structures, storm systems, temperature variations, and chemical signatures hidden below. Certain infrared wavelengths are absorbed by methane, while others pass through, allowing scientists to effectively slice through the atmosphere layer by layer, building a three-dimensional picture of what is happening at different altitudes. The gold coating on the mirror segments is not decorative. Gold is an exceptionally efficient reflector of infrared light. Aluminum, which coats Hubble's mirror, works well for visible wavelengths but reflects infrared less effectively. Every design choice on Webb, from the mirror coating to the sun shield to the operating temperature of the instruments, was made to maximize infrared sensitivity. The telescope operates at approximately -233 degrees Celsius, just 40 degrees above absolute zero. At this temperature, the telescope's own thermal emissions are minimized, preventing the instrument from drowning out the faint infrared signals arriving from distant targets. Hubble orbits Earth at an altitude of roughly 340 miles and passes in and out of Earth's shadow every 90 minutes. Webb orbits the Sun at the second Lagrange point, a gravitationally stable location approximately 1 million miles from Earth. At this position, the Sun, Earth, and Moon are always on the same side of the telescope, allowing the sun shield to block all three heat sources simultaneously, while the instruments on the cold side stare into deep space without interruption. Webb can observe a target continuously for far longer than Hubble ever could, and this capability would prove critical for studying a rapidly rotating planet like Uranus. Webb carries 4 primary science instruments, but 2 of them are particularly relevant to the Uranus observations. The near-infrared camera, known as NIRCam, is the telescope's primary imaging instrument. It captures detailed images at wavelengths between 0.6 and 5 microns, using a suite of filters that can be swapped in to isolate specific wavelength ranges. Different filters reveal different atmospheric features. One filter might highlight methane absorption while another penetrates to deeper cloud layers. By combining images taken through multiple filters, scientists can construct composite portraits of a planet that reveal far more than any single image could. The second critical instrument is the near-infrared spectrograph, or NIRSpec. Rather than producing images, NIRSpec splits incoming light into its component wavelengths, creating a spectrum that reveals the chemical fingerprints of whatever the telescope is observing. Every atom and molecule absorbs and emits light at characteristic wavelengths. By reading the spectrum, scientists can identify which chemicals are present, measure temperatures, and determine the physical conditions at different altitudes in an atmosphere. NIRSpec has a particularly powerful mode called the integral field unit, which can take spectra simultaneously across a 2-dimensional field of view. This means it can map the chemical and thermal properties of an extended object like a planet, producing not just a single spectrum, but a spatial map of spectra across the entire visible disk. For studying Uranus's atmosphere and ionosphere, this capability would prove transformative. On February 6, 2023, Webb turned near-cam toward Uranus for the first time. The telescope was approximately 1.8 billion miles from the planet at the time of observation. The imaging team used two filters, designated f140m and f300m, operating at 1.4 and 3.0 microns respectively. The exposure was relatively short, a necessary compromise because Uranus rotates once every 17 hours and 14 minutes. That rotation speed means atmospheric features and moons shift position noticeably within minutes. A long exposure would smear those features into blurred streaks. The team needed to capture a sharp snapshot, which limited how much light they could collect. Even with that constraint, the result was stunning. The image revealed Uranus's ring system with a clarity that no Earth-based or space-based observatory had ever achieved remotely. Before this moment, the rings of Uranus had been directly imaged by only two facilities in the history of astronomy. The first was Voyager 2, which photographed them during the 1986 flyby from close range. The second was the Keck Observatory in Hawaii, using its powerful adaptive optics system to partially compensate for atmospheric distortion. Ground-based radio and infrared observations had detected the rings indirectly through stellar occultations, watching distant stars blink as ring material passed in front of them. But actual resolved images showing the ring structure from nearly 2 billion miles away had been limited to those two sources. Webb's near-cam captured the rings in a single short exposure, with a level of detail that immediately made it the sharpest remote observation of the Uranian ring system ever taken. The rings of Uranus are nothing like Saturn's. Saturn's iconic ring system is broad, bright, and composed primarily of water ice particles ranging in size from grains of sugar to house-sized boulders. Those particles reflect sunlight brilliantly, making Saturn's rings visible through even a modest backyard telescope. The rings of Uranus exist in a different category entirely. They are narrow, dark, and composed of particles that reflect only a few % of the light that strikes them. The system consists of 13 known rings, each given a designation. The innermost rings carry numerical labels 6, 5, and 4, followed by rings designated alpha, beta, eta, gamma, delta, lambda, and the outermost, epsilon. The epsilon ring is the brightest and broadest of the group, but even it measures only about 12 to 60 miles in width depending on its position around the planet, compared to Saturn's main rings, which span roughly 45,000 miles from inner edge to outer edge. The Uranian ring particles appear to be composed of darkened organic material or radiation-processed ice, giving them an almost charcoal-like albedo. Some of the narrower rings are only a few miles wide, held in place by small shepherd moons whose gravity prevents the ring material from spreading out. The entire system is so faint that it was invisible in every photograph ever taken from Earth before 1977, and remained invisible in visible light images even after its existence was confirmed. Only in the infrared do these structures begin to reveal themselves clearly. In the infrared, however, ring particles emit thermal radiation and scatter infrared light in ways that make them detectable to Webb's sensitive instruments. The two-filter image in February 2023 showed the main rings glowing against the darkness of space, encircling the pale blue disk of the planet in a pattern that immediately communicated the extreme tilt. Because Uranus is tilted so far on its side, and because the rings orbit the planet's equator, the ring system appeared nearly face-on in the Webb image, a configuration that changes over the course of the planet's 84-year orbit as the geometry shifts relative to Earth's line of sight. But the rings were not the only revelation. The image also showed a prominent bright region on the sunward side of the planet, the North Polar Cap. This feature had been observed before by Hubble, a bright area associated with the pole currently tilted toward the Sun. It forms as part of the planet's seasonal cycle. As Uranus approaches solstice, and one pole receives direct sunlight for years on end, the atmosphere above that pole develops a distinct brightening, likely associated with changes in the aerosol and haze layers at high altitudes. Webb's infrared view revealed new detail within this polar cap, including a subtle brightening very near the pole itself that had not been clearly resolved before. At the edge of the cap, a bright cloud feature stood out distinctly. A second very bright cloud appeared on the opposite limb of the planet. These were not static features. They were evidence of active weather, convective processes driving material upward through the atmosphere to create visible cloud tops at altitudes where the surrounding atmosphere is relatively clear. 6 of Uranus's 28 known moons were also visible in the initial image, appearing as tiny bright dots scattered around the planet and its rings. Most of the moons were too small and faint to appear in such a short exposure, but the 6 that did show up demonstrated Webb's ability to detect extremely dim objects near a brighter target. This capability matters more than it might initially appear. The Uranian moons are among the least studied major satellite systems in the solar system. Unlike Jupiter's 4 large Galilean moons, which have been studied by multiple orbiting spacecraft, or Saturn's moons, which Cassini examined over 13 years of close encounters, the Uranian moons have been seen up close exactly once, during the Voyager 2 flyby in 1986, and that encounter, lasting only hours, returned images at resolutions that leave enormous gaps in our understanding. Most of the smaller inner moons were discovered by Voyager 2 itself, and have never been observed in detail since. Their sizes, compositions, and orbital dynamics are known only approximately. Some of the outermost irregular moons, discovered through ground-based surveys in the 2000s, have never been directly imaged at all. They are known only as points of light whose orbits have been tracked over multiple years. Webb's ability to detect 14 of the 27 known moons in its later, more comprehensive observation opened the possibility of using the telescope not just to study the planet, but to monitor its satellite system. By tracking moon positions over time, astronomers can refine orbital parameters. By measuring the brightness of moons at different infrared wavelengths, they can begin to constrain surface compositions, distinguishing between water ice, carbon dioxide ice, and darker organic materials that absorb infrared light differently. For the larger moons, Titania and Oberon, which are approximately 980 and 950 miles in diameter respectively, Webb might eventually be able to detect gross surface features or compositional variations across their disks, though the resolution from nearly 2 billion miles away would be extremely limited. Perhaps most intriguingly, the deep sensitivity of Webb's infrared detectors raises the possibility of searching for signs of activity at the moons, faint plumes of water vapor or ice particles that might indicate subsurface processes. Enceladus at Saturn was discovered to be actively venting water into space, and that activity was first detected through remote observations of its thermal emission and reflected light. A similar discovery at a Uranian moon, however unlikely, would be revolutionary. The February 2023 observation was technically a commissioning and early science image, not the product of a dedicated Uranus research program. It was intended in part to demonstrate Webb's capabilities for solar system science, but it immediately captured the attention of the planetary science community and the public. The image was compared directly to the Voyager 2 visible light photograph from 1986, and the contrast was dramatic. Where Voyager had shown a smooth, featureless blue-green sphere, Webb showed a textured world with visible structure, active clouds, a complex polar cap, and a ring system that practically leaped out of the frame. The comparison was slightly unfair because Voyager observed in visible light while Webb observed in infrared, and the 2 wavelength regimes revealed different things. But the visual impact was undeniable. Uranus looked like a real planet for the first time, not a smooth billiard ball drifting through the void, but a dynamic world with weather, structure, and complexity. Later in 2023, Webb returned to Uranus with a more comprehensive observation using additional NIR-CAM filters at multiple wavelengths. The expanded wavelength coverage allowed scientists to probe different atmospheric layers simultaneously, constructing a more detailed portrait than the initial 2-filter image could provide. The results added significant new detail. The North Polar Cap was captured with greater clarity, revealing not just the bright white inner cap, but also a dark lane running along the bottom edge of the cap at lower latitudes. This dark feature likely represents a region where aerosol properties differ, perhaps a boundary between the bright polar haze and the surrounding atmosphere. Several bright storms were resolved near and below the southern border of the polar cap, compact features that spoke to convective activity punching through from deeper atmospheric layers. The expanded observation also resolved the planet's outermost and innermost known rings simultaneously for the first time from any remote observatory. The outer rings, Epsilon, and the others discovered from Earth were clearly visible, but the most significant ring detection was the Zeta ring, the extremely faint and diffuse ring closest to the planet. The Zeta ring had been tentatively identified in Voyager 2 data but never clearly imaged from Earth or from space-based telescopes before Webb. It represents the innermost edge of the Uranian ring system, a region where ring particles are sparse and the reflected and emitted light is extraordinarily faint. Webb's sensitivity in the infrared was sufficient to resolve this ghostly structure, pulling it out of the darkness for the first time. For scientists planning a future Uranus orbiter mission, the Zeta ring observation was particularly valuable. Any spacecraft approaching Uranus would need to navigate through or near the ring plane. Understanding the distribution and density of ring material, especially the faintest components closest to the planet, is essential for mission safety and trajectory planning. The wider field version of the late 2023 observation was equally impressive. It captured 14 of Uranus's 27 known moons in a single frame, from the large classical moons Titania and Oberon down to tiny inner satellites like Perdita, Cressida, and Bianca, which orbit among the rings. The image also revealed a scattering of background galaxies far beyond the Uranian system, a reminder that even while observing a target within our own solar system, Webb's extraordinary sensitivity picks up light from objects billions of light years away in the same field of view. One aspect of the imaging observations that deserves attention is the sheer difficulty of capturing Uranus clearly. The planet's 17-hour rotation period means that atmospheric features, storms, and cloud structures move visibly across the disk within minutes. The inner moons, which orbit close to the planet and travel at relatively high speeds, also shift position rapidly. This creates a fundamental tension for observers. Longer exposures collect more light and reveal fainter features, but they also smear anything that moves during the exposure. Shorter exposures preserve sharpness, but sacrifice sensitivity. The Webb team had to carefully balance these competing demands, choosing exposure times that were long enough to detect the faint rings and dim moons, but short enough to freeze the planet's rotation and the moon's orbital motion. The fact that they achieved both goals simultaneously, resolving the Zeta ring while also capturing sharp atmospheric detail, testified to the precise planning and execution of the observing program. The infrared perspective Webb provided was not merely a prettier picture. It represented a fundamentally different way of seeing the planet. In visible light, Uranus appears as a nearly uniform blue-green sphere because methane in the upper atmosphere absorbs red and orange wavelengths while scattering blue light back toward the observer. This methane layer acts like a blanket, obscuring everything below it. In the near-infrared, different wavelengths interact with methane differently. Some infrared wavelengths are strongly absorbed by methane, which means light at those wavelengths cannot escape from deep in the atmosphere. Only light reflected from the highest altitudes, above most of the methane, reaches the telescope. Other infrared wavelengths pass through methane with minimal absorption, allowing light from deeper cloud layers to escape. By switching between filters that target strongly absorbed and weakly absorbed wavelengths, scientists can effectively view the atmosphere at different depths. A filter that selects a methane absorption band reveals only the uppermost hazes and the polar cap. A filter that selects a transparent window reveals clouds and storm systems at lower altitudes. Combining multiple filters into a composite image creates a layered view of the atmosphere, almost like peeling back the skin of the planet one layer at a time. This layered view is what transformed Uranus from a featureless disk into a world with visible weather. The bright cloud features detected by Webb are regions where material has been lofted to high altitudes by convective upwelling, rising columns of gas that punch above the surrounding methane haze and become visible in certain infrared wavelengths. The dark lane at the edge of the polar cap represents a region where the aerosol properties change, likely a transition zone between the chemically and thermally distinct polar atmosphere and the mid-latitude atmosphere. The storms near the polar cap border are evidence that the boundary between these atmospheric regimes is not smooth, but turbulent, a zone of dynamic activity where different circulation patterns collide. Think of it like shining different colours of flashlight through a layered cake. One colour gets absorbed by the frosting on top and bounces back immediately, showing you only the surface. Another colour passes straight through the frosting and reflects off the layer beneath, revealing structure hidden under the coating. A third colour penetrates even deeper, bouncing off the bottom layer before returning to your eye. By cycling through these different colours and noting what comes back from each one, you can reconstruct the internal structure of the cake without ever cutting into it. Webb's filter system does precisely this with infrared wavelengths and the methane-rich atmosphere of Uranus, and the timing of these observations was not incidental. When Webb first imaged Uranus in early 2023, the planet was roughly 5 years away from northern summer solstice. The North Pole was increasingly tilted toward the Sun, receiving more direct sunlight than it had in decades. The bright polar cap Webb captured was a feature of this seasonal moment, a haze of aerosols thickening and brightening in response to prolonged solar heating. If Webb had observed Uranus 30 years earlier, during the opposite season, the polar cap would have been on the other pole, and the atmospheric features would have looked completely different. Every Webb observation of Uranus is not just a portrait of the planet. It is a portrait of the planet at a specific moment in a seasonal cycle that takes an entire human lifetime to complete. These imaging observations established a critical baseline. They showed what Uranus looks like in the infrared at this particular moment in its seasonal cycle, as the planet approaches northern summer solstice expected around 2028. Future Webb observations taken months or years apart can be compared to these initial images to track how the polar cap evolves, whether storms increase or decrease in frequency, and how the ring system's appearance changes as the viewing geometry shifts. For a planet whose seasons last decades, this kind of long-term monitoring from a stable, sensitive platform is invaluable. But the imaging observations, as transformative as they were, had a fundamental limitation. They showed what the planet looks like. They revealed structure, features, and ring detail with unprecedented clarity, but they could not explain what was happening at the molecular and atomic level in the upper atmosphere. They could not measure temperatures at specific altitudes. They could not map the ionosphere where charged particles interact with the magnetic field. They could not detect the faint glow of auroral emissions shaped by that bizarre tilted offset magnetic dynamo buried somewhere in the planet's interior. For those measurements, scientists needed a different instrument and a different observing strategy. They needed to point the spectrograph at Uranus and watch it for hours, tracking the planet through nearly an entire rotation, capturing the faint infrared signatures of ions, glowing high above the cloud tops in a region of the atmosphere where the planet's magnetic field meets the solar wind. That observation was planned for January 2025, and when the data came back, it contained surprises that even the scientists who designed the program had not anticipated. The images had shown that Uranus was not boring. The spectrograph was about to show that it was genuinely strange, behaving in ways that existing models could not explain, cooling when it should not be, glowing when no one expected, and revealing the fingerprints of a magnetic field so contorted that it paints auroras across the sky in patterns unlike anything seen on any other world in the solar system. The images were only the beginning. What scientists found when they pointed Webb's spectrograph at Uranus for an entire planetary rotation was something no one had predicted. The forgotten planet was about to reveal that it had been hiding far more than a few rings and a polar cap beneath its quiet blue-green exterior. On January 19, 2025, the James Webb Space Telescope began a sustained observation of Uranus that would last 15.4 hours. This was not a quick snapshot like the imaging observations from 2023. This was a marathon stare, watching the planet rotate through nearly a complete day, capturing every shift in the faint infrared glow emanating from the uppermost reaches of its atmosphere. The observation was designed and led by Henrik Mellin of Northumbria University in the United Kingdom under JWST General Observer Program 5073. The instrument of choice was NIRSpec, the near-infrared spectrograph, operating in its integral field unit mode, which allowed the team to gather spectra simultaneously across a two-dimensional spatial field rather than from a single point. The filter and grating combination, designated F290LP G395H, covered wavelengths between 2.87 and 5.14 microns. This spectral window was chosen for a very specific reason. Hidden within that range of infrared light lies the faint emission signature of a molecule that would unlock the secrets of Uranus's upper atmosphere, H3+. H3+ is a molecular ion composed of 3 hydrogen atoms sharing 2 electrons. It forms when molecular hydrogen is ionized by solar ultraviolet radiation or by energetic particles funneled along magnetic field lines. Once created, H3+ emits infrared radiation at characteristic wavelengths as it rotates and vibrates. This emission is faint, incredibly so, but it carries encoded information about the temperature, density, and distribution of ions in the region where it exists. H3+ was first detected astronomically in Jupiter's atmosphere in 1989. On Jupiter and Saturn, it has been studied extensively as a tracer of auroral activity and magnetospheric interactions. On Uranus, it had been detected before from ground-based telescopes, but only as an average signal smeared across the entire disk. No one had ever mapped its distribution across the planet in detail. No one had ever measured how its properties changed with altitude. No one had ever watched it evolve over the course of a full Uranian day. The January 2025 observation was designed to do all 3 for the first time. The team used a 5-point cycling pattern to capture observations at the limb of the planet, the curved edge where the atmosphere extends above the visible disk against the blackness of space. By observing at the limb rather than looking straight down at the center of the disk, scientists can separate light coming from different altitudes. At the limb, the line of sight passes through the atmosphere at a steep angle, and emissions from higher altitudes are geometrically separated from emissions lower down. This technique allowed the team to build vertical profiles, measurements of temperature and ion density as a function of altitude above the cloud tops, extending up to 5,000 kilometers above the planet's visible surface. 20 individual observations were taken over the course of the 15-hour window, tracking the planet as it rotated and presenting different longitudes to the telescope. The cadence of these observations was carefully planned. As Uranus turned on its axis, different slices of the planet's atmosphere rotated into view. Longitudes that were on the far side of the planet at the start of the observation swung around to face the telescope hours later. By spacing the 20 observations across the full 15-hour window, the team ensured that nearly every longitude on the planet was captured at some point during the sequence. This is important because the magnetic field, which is tilted and offset from the rotation axis, creates different ionospheric conditions at different longitudes. Some longitudes are near the magnetic poles, where charged particles funnel down field lines and drive auroral emission. Other longitudes are far from the magnetic poles, where ionospheric conditions are quieter. Without observing a full rotation, the team would have seen only a partial picture, potentially missing the auroral bands entirely if they happened to be on the far side of the planet during a shorter observation. The 15-hour duration was not arbitrary. It was chosen to be as close to one full Uranian day as the telescope's scheduling constraints allowed. A Uranian day lasts 17 hours and 14 minutes. The 15.4-hour observation captured roughly 90% of a full rotation, enough to map the ionospheric properties at nearly all longitudes, while leaving only a narrow gap in coverage. The NIRSpec integral field unit added another dimension to this already rich dataset. Rather than collecting light from a single point on the planet, the integral field unit divided its field of view into a grid of spatial elements, each one recording a complete spectrum independently. This meant that for each of the 20 observations, the team obtained not one spectrum, but dozens of spectra from different positions across the planet's disk. Some spatial elements sampled the center of the disk, looking straight down through the atmosphere. Others sampled the limb, looking sideways through the atmosphere at a grazing angle. By combining the spatial and spectral information from all 20 observations, the team constructed a 4-dimensional dataset spanning 2 spatial dimensions on the planet's disk: altitude above the cloud tops extracted from limb geometry, and time as the planet rotated. No previous observation of any ice giant had produced a dataset with this level of combined spatial, spectral, and temporal coverage. The lead author on the resulting study, published in the journal Geophysical Research Letters in February 2026, was Paola Taranti, a PhD student at Northumbria University. Taranti and her colleagues processed the NIRSpec data to extract H3+ emission spectra from different spatial positions on the planet and at different limb altitudes. From these spectra, they derived the first ever vertical profiles of ionospheric temperature, volumetric ion density, and total H3+ emission for Uranus. What they found was a revelation. The temperature profiles showed that the ionosphere is not uniform. At all longitudes observed, temperatures peaked in a layer between 3,000 and 4,000 kilometers above the cloud tops. Below that altitude, temperatures were lower. Above it, they declined again. This vertical thermal structure had been predicted by some theoretical models, but had never been observationally confirmed at any ice giant planet. The peak temperatures implied that energy is being deposited into the upper atmosphere at specific altitudes, likely through interactions between the magnetosphere and the solar wind, particle precipitation along magnetic field lines, or wave-driven heating from below. The exact mechanism driving this temperature peak remains uncertain, but its consistent presence across all longitudes suggested it is a fundamental feature of the Uranian ionosphere rather than a localized anomaly. The ion density measurements were equally revealing, and in some ways more surprising. H3+ densities peaked at a lower altitude, near 1,000 kilometers above the cloud tops. The peak density reached values of approximately 4.45 times 10 to the 8th ions per cubic meter. This number might sound large, but it was actually significantly lower than what one-dimensional theoretical models of the Uranian ionosphere had predicted. The models, built from first principles and calibrated using the limited data available from Voyager 2 and ground-based observations, expected higher concentrations of ions at these altitudes. The discrepancy meant something was wrong with the models, either in their assumptions about the energy input to the ionosphere, the chemical reaction rates that create and destroy H3+, or the transport processes that move ions around. The observation did not just confirm existing understanding, it directly challenged it, providing hard observational constraints that theorists would need to incorporate into the next generation of atmospheric models. But the spatial distribution of the H3+ emission across the planet's disk was where the real surprises lay. 2 bright bands of auroral emission were detected, concentrated near the magnetic poles of the planet. On Earth, auroras form in rings around the magnetic poles as charged particles from the solar wind spiral along magnetic field lines and collide with atmospheric molecules, causing them to glow. Jupiter has brilliant auroras visible in ultraviolet and infrared, powered primarily by the volcanic output of its moon Io, which dumps tons of sulfur and oxygen into the Jovian magnetosphere every second. Saturn has its own auroral ovals, but Uranus's auroras are different from all of these, shaped by a magnetic field geometry that exists nowhere else in the solar system. Remember that the Uranian magnetic field is tilted nearly 60 degrees from the planet's rotational axis and offset from the planet's center by about 1/3 of the planet's radius. As Uranus rotates every 17 hours, this lopsided magnetic field swings through space, alternately opening and closing to the solar wind depending on the orientation. The auroral zones do not sit in neat circles around the geographic poles as they do on Earth. Instead, they sweep across the planet's surface in complex, constantly shifting patterns dictated by the interplay between the solar wind direction and the instantaneous orientation of the tilted magnetic axis. During a single Uranian day, the auroral regions migrate significantly in latitude and longitude. No other planet experiences this kind of rapidly evolving auroral geography. To picture how this works, imagine the solar wind as a steady river of charged particles flowing outward from the Sun in roughly the same plane as the planet's orbits. On Earth, the magnetic field acts like a deflector shield roughly aligned with the planet's spin. The solar wind hits this shield and flows around it, but the interaction is relatively stable because Earth's magnetic axis stays roughly pointed in the same direction as the planet rotates. On Uranus, the magnetic axis is tilted 60 degrees from the spin axis, and the spin axis itself is tilted 98 degrees from the orbital plane. As the planet rotates every 17 hours, the magnetic field swings through wildly different orientations relative to the incoming solar wind. Sometimes the magnetic poles face the solar wind head-on. 17 hours later, they are oriented sideways. The magnetosphere does not just wobble. It undergoes a complete geometric reconfiguration with every rotation, alternating between states where the field opens directly to the solar wind, allowing charged particles to flood in, and states where it deflects the wind more effectively. This means the energy input to the upper atmosphere changes dramatically over the course of a single day, driving auroral patterns that migrate across the surface in ways that no fixed auroral oval on Earth could replicate. The JWST observations captured this complexity directly. The two bright emission bands appeared at specific longitude ranges, between approximately 50 and 110 degrees west longitude, and between 220 and 290 degrees west longitude. These positions correspond to the regions near the magnetic poles, confirming that the auroral emissions are magnetically controlled. But the observation also revealed something unexpected between the two bright bands. In a longitude range between approximately 190 and 240 degrees west, there was a distinct depletion in both H3+ emission and ion density. This was not a gradual fading. It was a defined region where the ionosphere appeared to dim and thin, as though something was suppressing ion production or accelerating ion loss in that specific zone. The team interpreted this depletion zone as being linked to the topology of the magnetic field. In regions where the magnetic field lines transition from closed configurations, where they loop back to the planet, to open configurations, where they stretch outward into the magnetotail and connect to the solar wind, the physics of particle precipitation and ion transport changes. Closed field lines can trap charged particles and funnel them into the atmosphere, driving auroral emission. Open field lines allow particles to escape, reducing the local ion density. The depletion zone observed by JWST may represent a transition region where the magnetic geometry shifts from closed to open, creating a gap in the auroral emission. A similar phenomenon has been observed at Jupiter, where dark polar regions in the ultraviolet aurora correspond to areas of open magnetic field topology. The fact that an analogous feature appears at Uranus, despite its radically different magnetic field geometry, suggests that certain magnetospheric processes may be universal among magnetized planets, even when the underlying field configurations differ dramatically. Taranti described the significance directly. She noted that Uranus's magnetosphere is one of the strangest in the solar system, tilted and offset from the planet's rotation axis in ways that cause the auroras to sweep across the surface in complex patterns. Webb had shown for the first time how deeply those magnetic effects reach into the atmosphere. The three-dimensional mapping capability of NIRSpec's integral field unit made it possible to trace how energy moves upward through the atmosphere and to see the direct influence of the magnetic field on the ionospheric structure. No previous instrument had possessed the combination of infrared sensitivity, spectral resolution, and spatial mapping capability needed to achieve this. But perhaps the most unsettling finding from the January 2025 observation was not a new discovery at all. It was the confirmation and extension of a trend that scientists had been tracking with growing unease for more than 3 decades. Uranus's upper atmosphere is cooling. It has been cooling steadily since at least the early 1990s, when infrared observations from ground-based telescopes first measured the temperature of the H3+ emission layer. Each subsequent measurement over the years found the temperature a little lower than the last. The JWST observation recorded an average upper atmospheric temperature of approximately 426 Kelvin, roughly 150 degrees Celsius. This was lower than any previously published value. The cooling trend is puzzling because no one has a convincing explanation for it. The upper atmosphere of a giant planet is heated by several mechanisms. Solar ultraviolet radiation deposits energy directly into the thermosphere. Charged particles precipitating along magnetic field lines deliver kinetic energy that heats the gas. Gravity waves propagating upward from the deeper atmosphere can break and deposit energy at high altitudes, much like ocean waves breaking on a shore transfer energy to the beach. On Jupiter and Saturn, these mechanisms combine to produce thermospheric temperatures that are actually much higher than solar heating alone can explain, a discrepancy known as the giant planet energy crisis. Uranus has its own version of this crisis, but in reverse. Instead of being unexpectedly hot, its upper atmosphere is getting unexpectedly cold. The comparison with Neptune makes the mystery sharper. Neptune is often described as Uranus's near twin. The two planets have similar masses, similar diameters, and similar atmospheric compositions. They both orbit in the cold outer reaches of the solar system, yet their thermal behaviors could hardly be more different. Neptune's upper atmosphere is hot. It radiates substantial excess heat from its interior. Its weather is violently active, with wind speeds exceeding 1,200 miles per hour, the fastest of any planet. Uranus's upper atmosphere is cold and getting colder. It radiates almost no excess internal heat. Its weather, while more active than Voyager 2 suggested, is subdued compared to Neptune's. The same basic type of planet, in the same basic region of the solar system, is producing opposite thermal outcomes. Whatever mechanism is cooling Uranus's upper atmosphere, it is either absent at Neptune or overwhelmed there by the stronger internal heat source. Understanding why these twin worlds diverge so dramatically is one of the central questions in ice giant science, and the JWST cooling measurement sharpened the urgency of finding an answer. Several hypotheses have been proposed. One possibility is that changes in the solar wind over the past several decades have reduced the amount of energy being deposited into the Uranian magnetosphere and, by extension, into the upper atmosphere. The Sun has an 11-year activity cycle, and long-term trends in solar output could modulate the energy input to distant planetary magnetospheres. But the cooling at Uranus appears to be a steady decline rather than a cyclic variation, which makes it difficult to tie directly to solar activity patterns. Another possibility is seasonal. Uranus is approaching northern summer solstice, and the changing distribution of sunlight across the planet could alter atmospheric circulation patterns in ways that affect the upper atmosphere. The poles receive intense solar heating during solstice, while the equator receives almost none. This asymmetric heating could drive circulation cells that redistribute energy in the upper atmosphere, potentially cooling some regions while warming others. But this hypothesis remains speculative because we have never observed a full seasonal cycle with instruments sensitive enough to test it. A third possibility is more fundamental and more disturbing. It is possible that Uranus's weak internal heat source is connected to the cooling upper atmosphere in ways that are not yet understood. Uranus stands alone among the giant planets in radiating almost no detectable excess internal heat. Every other giant planet, Jupiter, Saturn, and even distant Neptune, pours out significantly more energy than it receives from the Sun, driven by internal processes that have been operating since the planets formed. Uranus does not. The reasons for this likely trace back to the catastrophic impact that shaped its interior billions of years ago, a subject that demands deeper examination. For now, what matters is that the upper atmosphere appears to be receiving less energy from below than comparable planets, making it more vulnerable to cooling if any external energy source diminishes even slightly. How this internal energy deficit connects to the observed atmospheric cooling is not yet clear. If the deep interior is sealed off and convection is suppressed, The upper atmosphere would depend almost entirely on external energy sources: solar ultraviolet radiation, magnetospheric particle precipitation, and wave heating from the lower atmosphere to maintain its temperature. A decline in any of these inputs, even a modest one, could produce the steady cooling trend that JWST confirmed. But testing this hypothesis requires understanding the interior structure, and that understanding remains out of reach without a dedicated mission. The JWST measurement added a new data point to the cooling curve and confirmed that the trend is ongoing, but it did not explain the mechanism. The observation was a diagnostic, not a solution. It told scientists precisely what the temperature is right now at different altitudes and longitudes across the planet. It gave them the most detailed thermal map of the Uranian ionosphere ever produced. But the underlying question, why is the seventh planet getting colder, remained unanswered. The combination of findings from the January 2025 observation amounted to the most detailed portrait of Uranus's upper atmosphere and magnetospheric interaction ever obtained. Vertical temperature profiles revealing a distinct thermal peak at 3,000 to 4,000 kilometers, ion densities significantly lower than models predicted, two auroral bands shaped by the offset, tilted magnetic field, a mysterious depletion zone between the bands linked to magnetic topology, and the confirmation of a decades-long cooling trend with no established cause. Each of these findings individually would have represented a meaningful advance. Together, they constituted a paradigm shift. The data showed that Uranus's upper atmosphere is more complex, more structured, and more dynamic than the sparse previous observations had suggested. The simple picture of a cold, quiet, magnetically confused world gave way to a layered reality of altitude-dependent heating, magnetically controlled auroral zones, and unexplained thermal evolution playing out over decades. The results also demonstrated something important about the observational technique itself. Ground-based telescopes had detected H3+ emission from Uranus before, but only as integrated averages. They could tell that the molecule was there and estimate a rough global temperature, but they could not map its spatial distribution or measure its variation with altitude. Hubble could image the planet in various wavelengths but could not perform the kind of deep infrared spectroscopy needed to isolate the H3+ lines. Only JWST, with its combination of infrared sensitivity, spectral resolution, spatial mapping through the integral field unit, and the ability to observe continuously from the thermally stable L2 orbit for 15 straight hours, could have produced this dataset. The observation was uniquely enabled by this telescope. No other facility currently in existence could replicate it. The time-lapse of Uranus assembled from the observation captured nearly a full rotation and revealed the planet as a living, changing world. The auroral emissions brightened and dimmed as different magnetic longitudes rotated into view. The polar cap gleamed. Faint storms flickered near the boundary between the polar haze and the mid-latitude atmosphere. The delicate rings caught the infrared light. The sequence of images, released publicly by ESA in February 2026, showed Uranus in a way it had never been presented before. Not as a static blue disk, but as a world in motion, rotating through its 17-hour day, its atmosphere glowing with the faint signatures of processes that had been invisible to every previous generation of instruments. Tiranti summarized the broader significance of the work by noting that revealing Uranus's vertical structure in such detail was helping scientists understand the energy balance of the ice giants. This understanding, she pointed out, extends beyond our own solar system. Ice giant-sized planets appear to be among the most common types of worlds in the galaxy based on exoplanet surveys. Yet Uranus and Neptune are the only ice giants we can study up close. Every detail learned about how their atmospheres work, how their magnetic fields interact with the solar wind, and how energy flows through their upper layers provides ground truth that can be applied to the interpretation of ice giant exoplanet atmospheres observed in distant star systems. What JWST discovered at Uranus is not just about one planet. It is about understanding an entire class of worlds that appears to dominate planetary populations across the Milky Way. The scientific community responded quickly. The results were published in one of the leading geophysical journals. Press releases from ESA and NASA highlighted the findings. The data was made publicly available for other researchers to analyze. Proposals for follow-up JWST observations were submitted, seeking to extend the monitoring over multiple epochs to track seasonal changes and to target specific atmospheric features in greater detail. The Uranus orbiter and probe mission concept gained another layer of urgency. Every new Webb observation sharpened the list of questions that only an in-situ spacecraft could answer. The three-dimensional map of the ionosphere was a first. No ice giant had ever been characterized in this way before, but every answer it provided opened deeper questions about a planet whose internal structure, magnetic dynamo, seasonal evolution, and atmospheric energy balance remain among the most poorly understood of any world orbiting our Sun. The eye had opened. It had seen things no one expected. And what it revealed was a planet far stranger, far more active, and far more mysterious than the quiet blue marble that had stared back blankly at every telescope pointed its way for more than 2 centuries. The questions were multiplying faster than the answers, and the biggest mysteries were still waiting in the dark. Every discovery the James Webb Space Telescope has made about Uranus leads to the same uncomfortable conclusion. We do not understand this planet, not in the way we understand Jupiter, whose atmosphere has been studied by orbiting spacecraft for decades, not in the way we understand Saturn, whose rings and moons were mapped exhaustively by the Cassini mission over 13 years, not even in the way we understand Neptune, which at least shares enough similarities with Uranus that models developed for one can sometimes be cautiously applied to the other. Uranus occupies a unique category in planetary science. It is a world where every new piece of data seems to deepen the mystery rather than resolve it. The Webb observations peeled back a layer of ignorance, only to reveal a deeper layer beneath, and beneath that layer another, descending into questions so fundamental that answering them may require technology and missions that do not yet exist. Start with the interior. Everything about Uranus's behavior, its feeble heat output, its bizarre magnetic field, its atmospheric dynamics, its unexplained cooling, traces back to what is happening beneath the cloud tops in a realm no instrument has ever directly sampled. The standard model of Uranus's interior divides the planet into 3 broad layers. At the center sits a small, dense core composed primarily of rock and iron, roughly half the mass of Earth. Surrounding the core is a thick mantle of hot, dense fluid composed of water, methane, and ammonia under extreme pressures. This is the layer that earns Uranus the designation of ice giant. Though the materials in this region exist in exotic high-pressure states, nothing like the ices of everyday experience. Above the mantle lies the gaseous envelope of hydrogen, helium, and trace methane that constitutes the visible atmosphere. This 3-layer picture is reasonable given what we know, but the details are profoundly uncertain, and the conditions inside the mantle push the boundaries of what laboratory physics can reproduce. At depths of a few thousand miles beneath the cloud tops, pressures exceed several 100,000 times the atmospheric pressure at sea level on Earth. Temperatures climb to thousands of degrees. Under these conditions, the water, methane, and ammonia that make up the mantle do not behave like any familiar substance. Water may enter a superionic state, a phase of matter in which the oxygen atoms lock into a crystalline lattice, while the hydrogen atoms flow freely through it like a liquid, carrying electric charge. This superionic water is simultaneously a solid and a liquid, a state of matter that was theoretically predicted in the 1980s, and experimentally confirmed in laboratory experiments using powerful lasers in 2019. If large regions of the Uranian mantle exist in this superionic phase, they would be electrically conducting, capable of carrying the currents that generate the magnetic field. The methane in the mantle faces equally exotic transformations. Under sufficient pressure, methane molecules break apart, releasing their carbon atoms. Those freed carbon atoms, subjected to crushing pressures and high temperatures, could theoretically compress into diamond. This is the origin of the diamond rain hypothesis, one of the most striking ideas in planetary science. Laboratory experiments using laser-driven shock compression have demonstrated that methane does indeed decompose and form diamond-like carbon structures at pressures comparable to those inside ice giant interiors. If diamond rain occurs inside Uranus, the diamonds would sink slowly through the surrounding fluid, falling toward the core and releasing gravitational energy as heat. This process, if it operates, would constitute a heat source analogous to the helium rain believed to occur inside Saturn. The fact that Uranus radiates almost no excess heat might mean that diamond rain does not occur there, or that it occurs at a rate too low to produce a detectable energy signature, or that the stratified interior prevents the heat from reaching the surface. Each of these possibilities has different implications for the planet's internal structure and evolution, and none can be confirmed or excluded without direct measurements that only an atmospheric probe and orbiter could provide. The most glaring uncertainty involves heat. Jupiter radiates approximately 1.7 times more energy than it receives from the Sun. That excess comes from the slow gravitational contraction of the planet. Jupiter is still shrinking, imperceptibly, and the gravitational energy released by that contraction heats the interior and drives convective motions that transport energy to the surface. Saturn radiates roughly 1.8 times its solar input, supplemented by an additional mechanism in which helium droplets rain through the metallic hydrogen interior, converting gravitational potential energy into thermal energy. Neptune, despite being farther from the Sun and receiving even less solar heating, radiates about 2.6 times what it absorbs. The excess heat drives Neptune's famously active weather, including the fastest sustained winds measured on any planet. Uranus breaks this pattern completely. Voyager 2 measured the planet's thermal emission and found no statistically significant excess heat above what the planet receives from the Sun. The upper limit was so low that it was essentially zero within the measurement precision. Uranus appears to be in thermal equilibrium with the Sun, radiating back only what it absorbs. For a giant planet that formed 4.5 billion years ago, from the collapse of gas and dust in the solar nebula, and should still be radiating residual formation heat, this is deeply strange. Where did all that primordial energy go? Why is Uranus not still cooling down like its siblings? The leading hypothesis, as mentioned previously, invokes the catastrophic impact that tilted the planet on its side. A collision violent enough to tip a planet with 14.5 times Earth's mass to an axial tilt of nearly 98 degrees would have deposited enormous energy into the interior. But the critical question is what happened afterward. One possibility is that the impact mixed the interior so thoroughly that much of the primordial heat was radiated away quickly in the aftermath, leaving the planet depleted of internal energy early in its history. A second possibility, and the one currently favoured by many modelers, is that the impact created a stable stratification in the interior. Heavy icy material sank to the bottom while lighter hydrogen-rich material floated to the top, creating a density gradient that suppresses large-scale convection. Without convection, heat from the deep interior cannot be efficiently transported to the surface. It is trapped, locked away beneath an insulating barrier, leaking out so slowly that it is undetectable. If this stratification hypothesis is correct, Uranus is a planet with a secret furnace buried deep inside it, still hot, still holding the energy of its formation, but sealed away from the surface by the very structure that the ancient impact created. This would explain the negligible heat flux measured by Voyager 2. It might also explain the peculiar magnetic field. On Earth, the magnetic field is generated by convective motion in the liquid iron outer core, a process called a dynamo. Vigorous convection is essential. The fluid must circulate in organized patterns driven by the combination of thermal buoyancy and the planet's rotation. If Uranus's deep interior is stably stratified and convection is suppressed throughout most of the mantle, then the dynamo must operate in a different region, perhaps a thin shell of conducting fluid at an intermediate depth where conditions still permit convective motion. A thin shell dynamo naturally produces the kind of magnetic field Voyager 2 observed, tilted, offset, and multipolar, because the geometry of convection in a thin shell is fundamentally different from convection in a deep, thick fluid layer. The magnetic field of Uranus may be the surface expression of an interior that was reshaped by violence billions of years ago and has never fully recovered. But this is still largely theoretical. We have no direct measurements of Uranus's interior structure. The gravitational field measured by Voyager 2 during its brief flyby provided some constraints on the density distribution inside the planet, but those constraints are broad. A dedicated orbiter measuring the gravitational field with modern instruments over hundreds of orbits could map the interior density structure with far greater precision, distinguishing between a fully stratified interior and one with partial convection, resolving whether the core is solid or fluid, and determining the size and location of the dynamo region. This is one of the primary science objectives of the proposed Uranus orbiter and probe. Without those measurements, the interior of Uranus remains a theoretical exercise constrained by a single flyby worth of data. The magnetic field itself poses questions that extend beyond its tilt and offset. JWST's detection of the auroral structure and the ionospheric depletion zone provided the first observational constraints on how the field interacts with the upper atmosphere from above. But the field's behavior deeper down, how it is generated, how it varies over time, whether it has undergone reversals or significant changes since the Voyager epoch, remains unknown. Earth's magnetic field reverses polarity roughly every few 100,000 years. Jupiter's field is relatively stable. Saturn's field is almost perfectly aligned with the rotation axis, which is itself a mystery that Cassini spent years investigating. Does Uranus's field change? Does the extreme tilt wobble over time? Does the offset drift? These questions cannot be answered by remote observation. They require sustained monitoring from orbit, measuring the field repeatedly over months or years to detect any temporal variation. The auroral observations from JWST opened another avenue of inquiry. On Earth, auroras are driven primarily by the solar wind, charged particles from the sun that interact with the magnetosphere and funnel down field lines to the poles. On Jupiter, the dominant auroral driver is internal, the volcanic moon Io injecting sulfur and oxygen into the magnetosphere. Saturn's auroras are driven by a combination of solar wind and internal plasma sources. What drives the auroras on Uranus? The JWST data showed auroral bands near the magnetic poles, which implies particle precipitation along field lines, but the energy source for that precipitation is not well constrained. Is it primarily solar wind driven? If so, the auroral brightness should vary with solar activity and with the orientation of the magnetosphere relative to the solar wind, which changes as the planet rotates. Or is there an internal plasma source, perhaps from the icy moons releasing water vapor that gets ionized and trapped in the magnetosphere? The Voyager 2 data originally suggested no significant plasma population, but the 2024 reanalysis showed that a solar wind compression event had likely cleared the magnetosphere of plasma just before the flyby. The normal state of the Uranian magnetosphere and the role of the moons in populating it with plasma remains an open question. This connects to one of the most intriguing possibilities raised by the Voyager reanalysis. If the moons of Uranus are actively contributing plasma to the magnetosphere under normal conditions, some of them may be geologically active. The 5 major Uranian moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all composed of roughly equal mixtures of rock and ice. Miranda and Ariel, whose fractured and resurfaced terrains Voyager 2 revealed decades ago, remain prime candidates for ongoing geological activity. The question is whether those processes, whatever drove them, are still operating today. Umbriel, Titania, and Oberon are older surfaced and more heavily cratered, but even they cannot be ruled out as geologically interesting given how little we know about the thermal and tidal dynamics of the Uranian system. In recent years, the discovery of subsurface oceans on moons throughout the outer solar system has transformed our understanding of where liquid water can exist. Europa, beneath its cracked icy shell, harbours a global ocean of liquid water in contact with a rocky seafloor. Enceladus shoots geysers of water vapor into space from its south polar region, fed by a subsurface sea. Even Titan, Saturn's largest moon, is believed to have a deep subsurface water ocean beneath its hydrocarbon-rich surface. The mechanism for maintaining liquid water on these worlds is tidal heating, the flexing of the moon's interior by gravitational interactions with the parent planet and neighbouring moons. Whether tidal heating operates strongly enough on the Uranian moons to maintain subsurface oceans is an active area of theoretical research. The orbital dynamics of the Uranian system are different from those of Jupiter and Saturn, and the heating rates may be lower, but they are not necessarily zero. Some models suggest that Ariel and Miranda, the moons closest to Uranus and most subject to tidal forces, could plausibly harbour thin subsurface oceans or pockets of liquid water beneath their icy crusts. If confirmed, this would place Uranus in the same conversation as Jupiter and Saturn when it comes to the search for habitable environments in the outer solar system. It is a tantalizing possibility that awaits a dedicated mission. JWST can observe the Uranian moons and potentially detect signs of outgassing or surface changes, but resolving the question of subsurface oceans requires close-range observations, gravity measurements, and magnetometer data from an orbiting spacecraft. The seasonal evolution of Uranus adds yet another dimension of complexity. The planet is currently approaching northern summer solstice, expected around 2028. At that point, the North Pole will be tilted most directly toward the Sun, and the southern hemisphere will be in the depths of its decades-long winter. Hubble observations spanning roughly 20 years, from the early 2000s to the early 2020s, have tracked the gradual brightening of the North Polar haze as increasing sunlight drives photochemical and aerosol processes at high northern latitudes. JWST captured this brightening with unprecedented clarity and spectral detail, but the observations represent only a brief window in a process that unfolds over an 84-year cycle. No modern instrument has observed even half of a full Uranian year. The planet was last at northern summer solstice around 1944, when the most powerful telescope available was the 100-inch reflector at Mount Wilson Observatory, and infrared astronomy did not yet exist as a discipline. The last equinox occurred in 2007, and observations around that time revealed unexpectedly active weather, including bright cloud features that had not been seen in previous decades. What happens as the planet moves past solstice and into the following equinox decades from now is unknown. Whether the polar cap will fade, whether new weather patterns will emerge, whether the atmospheric cooling trend will reverse or accelerate, these are questions that can only be answered through sustained observation over many years. This is where the value of JWST extends beyond any single observation. Each time the telescope observes Uranus, it adds another data point to a timeline that will eventually span significant fractions of the planet's seasonal cycle. If JWST operates for its planned minimum of 10 years, and potentially much longer given that its fuel reserves at launch were sufficient for roughly 20 years of station keeping, it could observe Uranus from the approach to solstice through the beginning of the long decline into autumn. Compared to the 84-year orbital period, even 20 years is a small fraction, but compared to what came before, it would be transformative. Before Webb, the longest continuous infrared monitoring of Uranus spanned a handful of observations per decade taken with ground-based telescopes fighting atmospheric interference. Webb offers the possibility of regular, high-sensitivity, high-resolution snapshots from a stable platform above the atmosphere, building a time-lapse record of planetary change that has never existed before. The proposed Uranus orbiter and probe would extend this capability dramatically. The mission concept, as outlined in the 2022 Decadal Survey, calls for a spacecraft that would travel to Uranus, enter orbit, and study the planet and its system for several years. An atmospheric probe would be released to descend into the cloud layers, directly measuring composition, pressure, temperature, and wind speeds at different depths. This probe would resolve fundamental questions about the planet's bulk composition. What is the ratio of hydrogen to helium? How much water is present below the clouds? What are the abundances of heavier elements? and how do they compare to the solar composition? These numbers are crucial for understanding how the planet formed and where in the solar nebula it originally assembled, before potentially migrating to its current orbit. The orbiter would map the gravitational field to determine the interior density profile. It would carry a magnetometer to measure the magnetic field at close range over extended periods, resolving its structure and temporal variability. It would perform repeated close flybys of the major moons, measuring their gravitational fields to determine whether subsurface oceans exist, imaging their surfaces at resolutions hundreds of times better than anything available from Earth, and searching for signs of geological activity. It would study the ring system at close range, determining particle sizes, compositions, and dynamics. And it would monitor the atmosphere and ionosphere continuously over a multi-year orbital tour, capturing seasonal changes, storm systems, and magnetospheric dynamics in a way that no remote telescope, however powerful, can match. The earliest projected launch window for such a mission would be in the early 2030s, utilizing a Jupiter gravity assist to reduce the travel time to Uranus. The geometry of this trajectory is dictated by celestial mechanics. To reach Uranus efficiently, a spacecraft must first fly inward toward Jupiter and use the giant planet's enormous gravity to accelerate and redirect its path toward the outer solar system. This gravity assist maneuver is not optional. Without it, a direct trajectory to Uranus would require either an impractically large rocket or a cruise time measured in decades rather than years. Jupiter must be in the right position along its 12-year orbit for the assist to work, which means launch windows open and close on roughly a decade-long cycle. The early 2030s window is considered particularly favorable. A spacecraft launched during this period could reach Jupiter within 2 to 3 years, swing around the planet, and then cruise outward to Uranus over the following decade. Even with that assist, the total travel time from launch to arrival would be approximately 13 years, placing the spacecraft in orbit around Uranus around the mid-2040s. 13 years is a long time to keep a spacecraft alive, powered, and functioning. Every electronic component, every mechanical actuator, every instrument must survive more than a decade of deep space radiation, extreme cold, and the slow degradation that affects all hardware over time. The spacecraft would need a radioisotope thermoelectric generator for power because solar panels are nearly useless at Uranus's distance from the Sun. Sunlight at Uranus is approximately 400 times dimmer than at Earth. A solar-powered spacecraft would need impractically large panel arrays to generate even modest amounts of electricity. Radioisotope power, which converts heat from the natural decay of plutonium-238 into electricity, is the only proven technology for missions at this distance. Communication presents another challenge. At Uranus's distance, radio signals traveling at the speed of light take roughly 2 hours and 40 minutes each way. Commands sent from mission control would not arrive at the spacecraft for nearly 3 hours, and confirmation of execution would take another 3 hours to return. The spacecraft must operate with a high degree of autonomy, executing pre-programmed observation sequences and making critical decisions about its own health and safety without real-time human intervention. Data transmission rates would be agonizingly slow compared to missions in the inner solar system. Returning the volumes of scientific data that a multi-year orbital tour would generate would require careful prioritization and compression, with the most scientifically valuable observations transmitted first. Budget constraints, competing priorities, and the complex politics of large space missions create significant uncertainty about whether this timeline will be met. The United States federal budget environment has introduced additional challenges, and some in the scientific community worry that the window for an efficient trajectory may close before funding is secured. If the Jupiter gravity assist opportunity is missed, the next comparable window would not arrive for over a decade, pushing arrival at Uranus into the late 2050s or beyond. This is the fundamental tension in Uranus science. The planet is changing in real time, approaching a seasonal milestone that occurs only once every 84 years. Scientists have the most powerful remote sensing instrument ever built, pointed at it and producing discoveries that are rewriting textbooks. but the deepest questions about interior structure, magnetic field generation, moon habitability, and atmospheric composition below the cloud tops cannot be answered from nearly 2 billion miles away. They require a dedicated mission that may not arrive for 2 decades or more. In the meantime, JWST is the best tool we have, and every observation it makes of Uranus increases the scientific return of the future orbiter by sharpening the questions it needs to answer and identifying the features it needs to investigate. There is something profoundly humbling about the state of our knowledge of Uranus. This is not a distant galaxy or an exotic pulsar at the edge of the observable universe. It is a planet orbiting the same star we see every morning. It shares a solar system with Earth. It formed from the same disk of gas and dust, coalesced under the same physical laws, and has been orbiting the Sun for 4.5 billion years, a quarter of the age of the universe itself. And yet we understand it less than we understand stars hundreds of light years away. We have mapped the surfaces of galaxies billions of light years distant in greater detail than we have mapped the atmosphere of a world in our own planetary neighbourhood. This disparity is not a failure of effort or interest. It is a consequence of distance, timing, and the practical limitations of exploration. The outer solar system is far away in ways that human intuition struggles to grasp. When Voyager 2 left Earth in 1977, it took nearly 9 years to reach Uranus, travelling at speeds exceeding 35,000 miles per hour. Light itself takes more than 2.5 hours to make the journey. Sending a radio command from Mission Control to a spacecraft at Uranus and waiting for confirmation that the command was received takes over 5 hours for the round trip. Operating a spacecraft at Uranus is an exercise in patience and planning on a scale unlike anything in the inner solar system. Every maneuver must be programmed in advance. Every observation must be anticipated. There is no real-time control, no quick corrections, no second chances. The Webb telescope sidesteps some of these challenges by observing from a fixed position near Earth, but it faces its own limitations. It can only observe what it can see from nearly 2 billion miles away. It cannot fly through the ring plane to measure particle densities. It cannot dip into the magnetosphere to sample charged particle populations. It cannot release a probe into the atmosphere. It cannot orbit the moons. For all its extraordinary sensitivity, JWST is still an eye looking from a great distance. It reveals surfaces and atmospheres and emissions. It cannot touch what it sees. And yet what it has revealed in just a few years of observation has fundamentally changed the conversation about Uranus. Before Webb, the ice giant was widely regarded as the least interesting planet in the solar system, a world that had been adequately characterized by Voyager 2 and that offered little to justify the enormous cost of a return mission. After Webb, that view is untenable. The planet that appeared featureless in visible light turns out to be a dynamic world of bright storms, evolving polar caps, intricate ring structures, and auroral displays shaped by the most geometrically complex magnetic field of any planet we know. Its upper atmosphere is cooling for reasons no one can explain. Its ionosphere is structured in ways that existing models did not predict. Its magnetic field paints auroras across the sky in shifting patterns that have no analogue anywhere else in the solar system. These discoveries matter beyond Uranus itself. Exoplanet surveys, particularly data from the Kepler Space Telescope and ground-based radial velocity programs, have revealed that ice giant-sized worlds, planets with masses between roughly 10 and 20 times Earth's mass, are among the most common type of planet in the Milky Way. They appear to outnumber both gas giants like Jupiter and Saturn, and small rocky worlds like Earth and Mars. Some estimates suggest that ice giant mass planets may be the single most prevalent category of planet in the galaxy, orbiting billions of stars across every type of stellar environment. Yet the only ice giants we can study in any detail are Uranus and Neptune, 2 planets in our own solar system that we understand less well than almost any other class of astronomical object. Every insight gained from JWST's observations of Uranus provides a template for interpreting the atmospheric spectra of ice giant exoplanets orbiting distant stars. When astronomers use Webb or future telescopes to analyze the atmospheres of transiting exoplanets in the ice giant mass range, they will need to understand what ice giant atmospheres look like, how they are structured, and how their properties change with temperature, composition, and magnetic environment. Uranus and Neptune are the only calibration points available. How does energy flow through an ice giant atmosphere? What role does magnetic field geometry play in shaping upper atmospheric structure? How do seasonal variations on extreme timescales affect cloud formation and atmospheric chemistry? What determines whether an ice giant radiates excess internal heat like Neptune or suppresses it like Uranus? These are questions with implications for every ice giant orbiting every star in the galaxy, and Uranus is the closest laboratory we have for investigating them. The story of Uranus and the James Webb Space Telescope is not a story with a neat conclusion. It is a story about the beginning of understanding. For 240 years, from Herschel's accidental discovery in 1781 to the early 2020s, Uranus was a world defined by what we did not know. JWST has begun to fill in some of those blanks, replacing ignorance with data, replacing assumptions with measurements, replacing the myth of a boring planet with the reality of a complex, dynamic, and genuinely mysterious world. But every blank that gets filled reveals 10 more behind it. The planet's interior remains unsampled, its full seasonal cycle remains unobserved, its moons remain unexplored, its magnetic field remains incompletely mapped, the cause of its atmospheric cooling remains unknown. JWST has shown us that Uranus is not the quiet, featureless world we assumed for decades. It is a planet of extreme seasons, impossible magnetic geometry, unexplained cooling, and atmospheric dynamics we are only beginning to observe. Its rings glow in the infrared. Its auroras shift and dance across the surface in patterns dictated by a magnetic field that defies simple explanation. Its ionosphere is layered and structured in ways that challenge the models built to describe it. And somewhere deep inside, sealed beneath billions of tons of compressed ice and fluid, a dynamo churns in a thin shell, generating a magnetic field unlike any other in the known solar system, powered by processes we cannot directly observe and do not fully comprehend. The outer solar system is not finished surprising us. The most profound mysteries in the universe are not always the farthest away. Sometimes they orbit the same star we do, hiding in plain sight at the edge of naked eye visibility, waiting for the right instrument and the right moment to reveal what they have been concealing for billions of years. Uranus waited patiently through centuries of neglect. Now, finally, we have begun to look. And what we have found is not answers but better questions, deeper puzzles, and a renewed sense of wonder at a world we thought we knew and never really did. We have barely begun to look, and the ice giant is only beginning to show us what it holds.